Here's a relatively quick thermodynamics problem which looks at a PV diagram and, well, it actually looks at a cycle, a thermodynamic cycle drawn on a PV diagram for which we can see the four states, but we only know the temperatures for three of them, and we somehow have to deduce the temperature for the fourth state, right? So we have the temperatures for states 1, 2, and 3, and we have to find the temperature for state 4. And this is literally the only thing we know. We don't know what gas is, we don't know any pressure ratios, volume ratios, or anything like that. We only know three temperatures and we have to find the fourth one. And this is the kind of question that you might see as an undergraduate student if you're doing thermodynamics in your first year, or you might even see it in your high school. For instance, if you're preparing for some, let's say, some serious physics competition. And if you have any other ideas or if you would like to see anything similar to this on the channel, let me know in the comments. So let's read the question and then we'll try solving it as usual. So for the thermodynamic cycle on the, well, it's on the same page in this case, the following state properties are known. So as I said, we know three temperatures, we know 300, 400, 500, and we have to find T4. And that's the problem. So what I would do here is I would start from state 1 and I would go from state 1 to state 2, and then I will try to write some thermodynamics relationships and see where this takes us. So 1, 2 is a constant volume process, right? So this is isochoric, or constant volume, and for an isochoric process we have that P1 over T1 is equal to P2 over T2. Okay, now we know T1 and T2, but what this actually allows us to do is to get, a relationship between P1 and P2. So we have, let's say, P2 over P1 equals T2 over T1, which is nice. We don't know if we're ever going to use this, but we're going to call this equation 1. Okay, so let's move on to the next process, which is 2-3. And 2-3 this time is an isobaric process. So this is constant pressure. So we've got an isobaric process, and the relationship, of course, is V1 over T1 is V2 over T2, also known as V2 over V1. If we rearrange, that is actually, that's not V1 and V2, that is V2 over T2 is equal to V3 over T3, I meant. Which means that V3 over V2 is equal to T3 over T2. Okay, again, we don't know if we're ever going to use this, but that's what we have. And we're going to label this equation 2. And then if we go from 3 to 4, so 3 to 4 is similar to 1, 2, right? It's another isochoric process. And like all isochoric processes, we have P3 over T3 is equal to P4 over T4. So we have P4 over P3 equals T4 over T3. Now, if you think about it, P4 is the same as P1, right? Because they're sitting on the same horizontal line. They have the same y coordinate. So we can actually write that here, which is P4 is equal to P1. And in the same way that P4 is equal to P1, P3, so this is equal to P1, and P3 is equal to P2, right? So we have P3, you have P2, they have the same y coordinate, which means that this is going to equal P2. So P4 over P3 suddenly turned into P1 over P2, which is equal to T4 over T3. Okay, now this may not be this may not seem useful, but if you remember from what we had in the first for the first state, we already had an expression for P1 over P2 or P2 over P1. So we have P2 over P1. Let's write that here. So besides this, P2 over P1 is also equal to T2 over T1. T2 over T1, like that. So if we combine those together, we should be able to get something nice out of it, which is the following. So P1 over P2 is T4 over T3, but P1 over P2 can also be written using this. So P1 over P2, if we, flip both fractions, this is going to be T1 over T2. So T4 over T3, which is P1 over P2, is equal to this P1 over P2, which is T1 over T2, which means that T4, which is the temperature we've been looking for, is T3, T1 over T2. And that's the expression which gives us the fourth temperature. And as you can see, it only depends on the three temperatures that the problem gives us. So if we put the numbers in, we get T3, so that's 500 multiplied by T1, which is 300 over T2, which is 400, and then we can cancel those out, and we have 500 times 0.75 times 3/4, and this is going to be 300. So the final answer is 375 Kelvin. Okay, which, if you think about it, kind of makes sense for this temperature at 4 to be less than the temperature at 3. Because if this was something like a Brayton cycle, the highest temperature would be here, and after the combustion chamber, you would have the turbine, and after the turbine, the temperature drops. So end up with something like this, which is a lower temperature. So we have this cycle is similar to something related to an engine, in the sense that the temperatures or the order of the temperatures kind of makes sense, right? So you have the lowest temperature here, and then you can have a compression of sorts, but the volume stays constant in this case, so it's not really that. And then you have a heat addition, and then you have an expansion perhaps, and you're at P4, or you're at state 4, which has a lower temperature than 3. So using those, we found that the missing temperature was 375 Kelvin, and that's the end of the question.